of the different arrangements which can be made by taking some or all of the given number of things is called permutation. But each of the different selections or groups which can be formed by taking some or all of the given number of things is called combination. So let's say I take an example. So let's say I have 3 balls labeled 1, 2, and 3. Now what I do is I have been asked to take permutation of any of the 2 balls from these 3 given balls. So I can take either 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2. So when we are talking about permutation, we essentially mean the arrangements, which means 1, 2 and 2, 1 are 2 different arrangements. So they are 2 separate entities. But if we are taking combination of 2 balls from these 3 labeled balls, then 1, 2 and 2, 1 are basically the same selection. So they are the same entity, which is why in case of combination, we'll essentially have 3 combinations: 1, 2, 1, 3, and 2, 3. Naturally, the number of combinations of things taken at a time will be less than the number of permutations taken at a time. So the next thing that we'll be covering is a fundamental principle of association. Now, the fundamental principle of association states that if an operation can be performed in n ways, and after it has been performed, another second operation can be performed in n ways, then both of the operations can be performed in m cross n ways. So let's say I have 2 types of balls. Some balls are colored and some other balls are labeled. So I have 4 colored balls, namely red, green, yellow, and blue, and 5 labeled balls, labeled 1, 2, 3, 4, and 5. Now I'm asked to take 1 red ball, 1 colored ball, and 1 labeled ball at a time. So what I can do is I can take a red ball, and with the red ball I can take ball 1, ball 2, ball 3, ball 4, or ball 5. So for each of the colors taken from this set of colored balls, I'll have 5 options of labeled balls to choose from, which means I have in total 4 into 5 ways in which I can draw 1 colored ball and 1 labeled ball. The next thing that I need to note is fundamental principle of association can be extended to more than 2 operations. So let's say I have colored balls, labeled balls which are labeled in numbers, and balls which are labeled in terms of letters. So let's say A, B, C, D, E, F. So I have 6 balls labeled in English letters. So I'll have one number chosen for each lettered ball and each colored ball, which means I have 4 cross 5 cross 6 ways in which I can draw these balls. So this fundamental principle of association can essentially be extended to more than 2 types of operations. Next, we move on to the formulae that are essential for solving permutation sums. So the first thing that we'll do is n things taken r at a time. So let's say I have n number of things and somebody has asked me to take r of them at a time. So the first time that I draw, let's say I have n balls. Let's say I have to draw 1 ball for the first draw of a ball. I can get n options. So I can draw the first ball, the second ball, up to the nth ball. So for the first draw, I have n options. Now the next draw, I actually have n-1 options because I cannot choose the first ball that I've already chosen. So I have to exclude that ball and I have n-1 options to choose from in my next turn. Similarly, in my third term, I have n-2 options to choose from because I have already drawn the 2 balls in my first 2 draws. So I cannot choose those 2 again. So I'll have to choose between the remaining n-2 balls. Up to like continuing this procedure of thought process, for my r8th draw, I'll have remaining n-r-1 options to choose from. You see, in the second term, in the second draw, I have n-1 options to choose from. In my third, let me write that down first. So in my second draw, I have n-1 options to choose from. In my third draw, I have n-2 options to choose from. Naturally, in my r8th draw, I'll have n-r-1 options to choose from. So the subtracted number is always 1 minus the drawing number. So I just break the bracket here and I write it as n into n-1 into n-2 into n-r plus 1. Let me just underline that properly. Yeah. The next thing that I do is I multiply this expression n minus r into n minus r minus 1 into 3, like n minus r minus 2, going on up till 3 into 2 into 1, both in the numerator and the denominator. Now, if I particularly see the numerator, I'll see that it is basically in the reverse form. It is a multiplication of 1 into 2 into 3 into 4 up to n minus r minus 1 into n minus r into n minus r plus 1 up till n. So that is basically n factorial. Similarly, in the denominator, if I take it in the reverse order, I'll get 1 into 2 into 3 up to n minus r. So that is basically n minus r factorial. Now this n factorial by n minus r factorial can be notationally expressed as npr. So the numerator is written as the superscript on the left hand side of the letter p, because we are talking about permutation, and the number that is subtracted from the number on the numerator is written on the subscript right hand side of the letter p. So this notation is basically npr. Now, as a corollary of the previous formula, we have let's say a formula, n things taken all at a time. So as you can see, in my first case, I had n things taken r at a time, and I reduced that to npr. So if I replace n things taken n at a time, that essentially means n things taken all at a time. So what I essentially do is I replace r with n, and I get npn. Now, if I take n things taken all at a time, it means I am rearranging those n terms within themselves. So basically this npn represents n things arranged among themselves. So let's say I take one thing out of the n things and I can put them in n positions. The next time I'll have n minus 1 positions. For the third item, I'll have n minus 2 positions. Naturally, when I arrange the n things among themselves, I essentially have n factorial ways in which I can arrange them. So this is basically npn is equal to the n things taken all at a time, which is equal to n things arranged among themselves, which is again equal to n factorial. Moving on to the next formula, we have n things where p are of same kind, q are of another kind, and r are of a third kind. So let's draw that pictographically. So let's say I have n number of things. I have small n number of things, of which let's say there are n number of balls, and I need to choose some combination of some permutation of balls from them. I need to choose n number of things. So what I notice is, of these small n number of balls, there are p balls which are red in number. P balls which are red in number, q balls which are let's say blue in number, and r balls which are, let's say, green in number. So taking all of the n things together, I can arrange them in n factorial ways as discussed before. However, since there are p balls which are identical in nature, I have rearranged themselves, which are essentially the same permutations. So I have increased my number that I originally need. So what I'll do is I'll divide the number that I've got, n factorial, and I'll divide it by p factorial, because those p identical balls can be arranged among themselves in p factorial ways, which I have repeated. They are identical permutations, and I have included all those identical permutations in my answer. Using the same theory, I'll be dividing it by q factorial as well as r factorial. So when there are repetitions, I will take all of the I'll take all of the items. At the beginning, I'll take all of them as different items, and then I'll divide them by the number of repetitions or number of identical items in the group. Moving on, we have n things where taken r at a time. Let me just n things taken r at a time. Each thing may be repeated once, twice, up to r times in an arrangement. The difference between this and the previous exercises or formula that we discussed was, when we are taking the first item, in my second draw, I cannot include the item that I've already drawn. But in this case, I can do so. So in my first draw, I have n options. In my second draw, instead of having n minus 1 options, I again have n options. So I can include the ball that I already drew. So in my first option, I have n. In my first draw, I have n options. In my second draw, I have again n options. And similarly, in my rth draw, I'll again have n options. So this is basically n into n into n up to r. So that's n to the power r. Next thing is n things taken r at a time, in which n particular things never occur. So let's say I have n number of balls which I want to take R balls from, but I do not like, or maybe let's say M balls are broken. So I do not want those M balls in my set of R balls. So what I do is I essentially remove those M balls that I don't want. So the M particularly things that never occur, I remove these M things from my original N number of balls, and I'm essentially left with N minus N number of balls from which I need to draw R balls. So that's just a pure intuition of saying that n things taken are at a time in which m particular things never occur. The answer will be n minus m pr. Next thing is m particular things always occur. So let's say I have some m favorite balls which I always need to occur, which always needs to occur in my R set of balls. So what I do is I remove those m balls that I want in my group. So since I've already chosen m balls in my R balls, I just need to choose R minus m more balls from n minus m set of things. So let's say let's say this is my set of small n things, and I want m number of balls always to be there. So this is n and this is m. Now I already have selected this m number of balls, so I just need r minus m more balls from the remaining portion. So I have n minus m p r minus m. Now this r p m, this is basically the position of m that I need to choose. So let's say I have r blanks that I need to fill using my balls that I have selected. I need to choose which positions these m already selected balls need to move on. So there are r options and I need to choose m positions out of them. So this essentially represents the let's say the determination of position of the m things that I had originally chosen. The next thing is m particular things are placed in m places in a definite order. The difference is, in the previous example, I had to choose in which positions those m particular things will go. But here they have been given a definite order. So in my question, they have probably told me that my first ball will go in this position, my second ball will go in this position, and my third ball will go in this position. So I cannot choose that position. So this REM thing, that will not be there. So I'll just be remaining with this bracketed portion. In the third, in the B, let's say the B formula part, m particular things are placed in m places in any order. So in this case, what they have is when they talk about in a definite order, they have already said that the first ball will be in this position, the second ball will be in this position, and the third ball will be in this position. But when they talk about it placed in m places in any order, they have probably said that the m balls that I always want to have in my set of R balls, they need to be in first position, third position, and fifth position. These m balls can take any of those places, but they need to be in these places only. They cannot be in the second and the fourth positions, but they can be anywhere in the first, third, or fifth position. So basically we have been given these m number of position in which the m balls need to be. So we can arrange those positions among themselves in m factorial ways. And going by the previous logic, I already have the other positions of the remaining r minus m balls that need to be chosen from n minus m balls. The final thing is m particular things come together in a given order. Using the same formula or the thought process, I already have n minus m p r minus n. Now this m particular things come together in a given order. So instead of having separate positions for the m things, I essentially have, let's say I have grouped those m things into a separate entity. So let's say I always want my 5 favorite designed balls to be in a separate group. So what I do is I have those R set of balls that I have selected, and my favorite M balls, I take them as a separate entity. I put them in a packet, and I consider that to be a different identity itself. So I essentially remove those M balls. So I have R minus M balls. I put those M balls in a packet, and then I put it back in my set of balls. So essentially I have R minus M plus 1 number of things. And that is how I get my answer.